Hello, this is the third video of a fifth vector series on lines and planes for OCR Pure Core Further Mathematics, and we will find the perpendicular distance from a point to a line in 3 dimensions. Given a point A, which will be x, y, z in 3 dimensions, and a line in 3 dimensions, so try and visualize this diagram as being in 3D. We may want to find the perpendicular distance from A to L, let's call that D, or the coordinates of a general point X on the line L. Unlike the 2D situation, we are not given a formula for finding the perpendicular distance. But we note that the shortest distance in 3 dimensions is still the perpendicular distance. Therefore, the vector from A to X still needs to be perpendicular to this line L, and this fixes this point X. Once we know x, then we can find ax, and hence the magnitude of ax will give us the distance that we're interested in. In this example, we're asked to find the shortest distance from the point A, 3, 1, minus 1, to the line joining two other points, P and R, given as shown. Let's see what we need to work out. We know that the line will be L, will be in effect the line PR. And we know that this will have X lying on it, where X is going to be a perpendicular distance away from A, which is 3, 1, minus 1. So let's find that L equation. Let's use this R equals A plus lambda D format. So let's jump on the line at R, 1, 0, 2, and then we'll be moving along that line, give it parameter mu, and in the direction of P minus R. So 6 minus 1 would give us 5, 13 minus 0, 13, 5 minus 2, 3. We've kept those positive because of course the parameter mu can take negative or positive values. And we can then write x, y, z components as 1 plus 5 mu, 13 mu, and 2 plus 3 mu. So this is the vector equation for our line L. Alright, so let's have a look at what the vector AX would look like. We know from up here that A is 3, 1, minus 1. So then AX will be this 1 plus 5 mu minus 3, 13 mu minus 1, and 2 plus 3 mu minus 1, which if we tidy it up gives us minus 2 plus 5 mu, minus 1 plus 13 mu, and 3 plus 3 mu. So how do we choose the value of mu which will fix x to make sure that AX is perpendicular to L? Well, we're going to use this useful idea that the scalar product is 0 for two perpendicular vectors. Right, do we know the direction of the line? Well, yes we do, because we've got the direction of the line is the 5, 13, 3, right, or the D part, which we can see up here. So if we look at the vector product of AX with D and set that equal to 0, that will enable us to find the value of the parameter mu and fix x. And this is what we've done on this slide here. So we've got AX dot product with the direction vector of the line, set it equal to 0 because we're using this idea that the scalar product of two perpendicular vectors is 0. And that leads us to the minus 10 plus 25 mu minus 13 plus 169 mu plus 9 plus 9 mu equals 0, which will then give us the value that mu is 14 over 203. This then allows us to identify where x is. And it also enables us to look at this AX. We put those mu values in, we will have identified AX. Okay, so these values here have been obtained using mu equals 14 over 203, which weren't particularly nice calculations, but we're fine using a calculator. Then, now we know AX, we can find the modulus of AX, and this will give us this perpendicular distance D. So, keeping out the fraction part 1 over 29, we've just used the normal Pythagoras to find that perpendicular distance, and it turns out to be 3.61 to 3 significant figures. Okay, so an alternative method would have been to have found the distance or the vector OX and AX as before, and then once we'd got to the point where we knew that the vector AX could be written in this form, then to use calculus to minimise this expression, or the length of AX squared. So we could differentiate that and set it to 0. So this is what we'd get by differentiating this expression here with respect to mu. Set it equal to 0, and as expected, we get the same value for mu, which fixes x. We can then use that back in this equation for ax squared and then square root it, getting the same overall result. In the next video, we will look at how to find the perpendicular distance between two parallel lines.